Waves. One of the first things we need to know about waves is there are two different types of wave. One shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. The electromagnetic spectrum. Light is actually an electromagnetic wave and is part of a whole spectrum of waves called the electromagnetic spectrum. The waves all have certain things in common. They all travel at the speed of light in a vacuum, and they can all be reflected, refracted and diffracted. So, how are the different parts different? Well, it's the frequency and the wavelength that change. So, here on the screen is the electromagnetic spectrum. We have radio waves on the left. They have the longest wavelength and the lowest frequency. And as we move from left to right, the wavelength decreases and the frequency increases. Also, the energy the wave carries increases as well. Now, next to radio waves is microwaves. Then we have infrared, followed by visible light, which is right bang in the middle of the spectrum. Then we have the high energy side with ultraviolet, X-rays, and finally gamma rays. You need to memorize this spectrum and know how the wavelength and frequency change as you move along it. Okay, let's look some more at the lower energy half of the spectrum, from radio waves up to visible light. All these parts of the spectrum are used in communications. Radio waves are used for sending TV and radio signals, both short and long distances. Really short wavelengths are used for very short distances, and the longer wavelength for longer distances, as they can reflect off a layer of charged particles in the atmosphere called the ionosphere. However, radio waves can't pass through the ionosphere, so if we want to communicate with satellites, we must use microwaves, as they will easily pass through the ionosphere. Microwaves are also used in mobile phones, and certain wavelengths are absorbed strongly by water molecules and so are used to cook food. These are not the wavelengths, however, that are used in mobile phones. Infrared, as we know, carries heat and can be used in thermal imaging and for grills for cooking, and it is also used in communications, as is visible light, both being sent down optical fibers. So all these 4 lower energy electromagnetic waves are used in communication. But is there any danger in using them? Well, at the moment, there is no scientific evidence that any of these parts of the EM spectrum pose any danger whatsoever, apart from maybe getting burnt by infrared. Now let's move on to look at the high energy part of the spectrum. So what are these used for? Well, ultraviolet is used in sunbeds to help you get a suntan. And it's also used in special security inks because they absorb ultraviolet and emit visible light. X-rays, obviously, are used to look for broken bones in hospitals. And finally, gamma rays are used to kill bacteria in food, to keep it fresh longer, to sterilize surgical equipment, and also to kill cancer cells in radiotherapy. Now, this is the high energy part of the spectrum, so there are dangers with using these. As you know, too much exposure to ultraviolet can cause skin cancer. Now, X-rays and gamma rays are even more dangerous, as they have enough energy to remove an electron from an atom, creating an ion. We call this ionization. And this can really damage cells and can actually kill them or cause mutations in them, leading to cancer. So exposure to high doses of X-rays and gamma rays really needs to be minimized. It's okay when you're just going for 1 or 2 X-rays at the hospital, but it's why the people working in the hospitals need to take extra precautions to minimize their dose. And that is the EM spectrum. Make sure you learn the entire electromagnetic spectrum and the uses and dangers of each part.